Assalamualaikum and greetings to Madam Norzalina and my fellow friends. Today, I'm Nohajikul Iqbal bin Yusuf with my friend Nazwan Iskandar bin Gapar and Muhammad Harith Adib bin Muhammad Haidi. We're going to be presenting our group assignment for MAT 575. Next, we'll be going to the introduction. Okay, now we'll be going to the introduction. Estimating the area of regular shape is a common problem in science and engineering. For complex natural objects like biological specimen, which is like a living thing, a standard geometry formula does not apply to it. So numerical methods are used instead. So in our assignment, we are applying numerical integration technique that we have learned in our classes, which is MAT 575, to estimate area of an image that we have selected from an internet. For our group, we will be choosing the image of a snakehead fish and we will be dividing it into 12 segments so that the calculation will be much accurate. Okay, next we'll be going to problem statement. For the first problem statement is the fish body has an irregular shape that cannot be represented by simple geometric formulas. This is direct calculation of its cross-sectional area is difficult due to the non-uniform outline. So from this one, we can see that the fish has a unsymmetrical shape and its shape cannot be the area of its body cannot be calculated with equations such as for rectangle or any polynomial shape that we have today. Next is each fitted polynomial must be expanded and integrated analytically, which involve large intermediate value that are prone to arithmetic error. And lastly is different segments of the boundary have different data characteristic with varying node spacing, number of point and curve behavior. Therefore, no single numerical method is suitable for assessment. This is the reason why we have divided the fish images into two different segments so that we can use different analytical methods to calculate the area.
Moving to objective. The first objective is data collection, which is turning the physical image profile like a fish into the discrete XY data points and divide the fish boundary into 12 segments. Secondly, curve fitting, which is the polynomial interpolation for Lagrange and Newton's method, and regression analysis, which is for the least square. The third one is area calculation. To integrate each separate segment, fitted polynomial function over the boundary interval to calculate the cumulative enclosed area. Moving to methodology. The first one is preparation of the fish image. The fish were pasted onto the graph paper and then be point x and y coordinate where it will be recorded directly from the graph paper to the table. Next is segmentation. The fish boundary was divided into 12 segments, and the total area of the fish is the upper segment area minus the lower segment area. The third one is numerical method. The numerical method we were using is Lagrange interpolation, least square approximation, Newton's divided difference interpolation. The last one is integration procedure. Expand the fitted polynomial and compute the antiderivative, then evaluate the definitive integral, which is the area, the upper part with minus the lower part.
Then we go to the result. Now in result, we first printed the picture of a fish that we wanted and pasted it onto a graph paper. We then divide it into segments, and for each segment, we plot 4 to 5 points so that we will be able to use uh, mathematical equation or numerical equation to get the area for the fish. This is for the segment summary. We basically divide the fish into 12 segments, but in segment 1 and segment 12, we have divided it into 3 more segments, which is 1.1, 1.2, and 1.3, and also 12.1, 12.2, and 12.3. This is to get a more accurate areas and does not include any blank area which is not necessary and not the part of the fish. Next, we'll be going to the first segment for the fish images. For the first segment, I have divided it in 3 other segments, which is 1.1, 1.2, and 1.3. In 1.1, we in 1.1, 1.2, and 1.3, I use Lagrange method. For Lagrange method, we first need to get out the Lagrange equation. Then we substitute any value that we can from the table into the equation and expanded it one by one. After we expanded it, we add the same power of variable and we get the final polynomial equation. After we get the final polynomial equation for the segment, we then integrated it with the lowest value of x to the highest value of x to get the area of the segment. For segment 1.1, the area will be subtracted with 1.2 to get the area for the mouth, upper mouth of the fish. As I said before, the area in 1.2 segment also use Lagrange method, and the area that we get from this, we use it to get the area of the upper mouth of the fish. For segment 1.3, we still use Lagrange and the same method and expansion and integration, but with different value from the table. The value from the segment 1.3, we will use it to subtract with segment 12.3. In this value, we will get the segment for the body of the fish.
Okay, now for second segment. For second segment, we use Newton divided difference interpolation. There are two types of interpolation for Newton. The first is forward, second is backward. But for second part, we use Newton forward divided difference. First of all, from the data XY table, there are 4 points of data. Therefore, the degree is 3. So 4 minus 1 equal to 3. M equals to 3. First, we form the divided difference table and only until third divided difference. To form the table, first, we form the X, F, first divided difference, second and third divided difference. To get the first divided difference, for example, we calculate the data from X and Fx. For example, 33 minus 30 equal to 33 minus 30 divided by 31 minus 25 equal to 0.5. And the letter 35 minus 30 divided by 38 minus 31, we get 0.2857. And also the same for the last, for first divided difference. For second divided difference, we calculate by 0.2857 minus 0.5 minus 38 minus 35, 25. So data from first divided difference divide x, we get the second divided difference. Also the same for third divided difference. 0.0408 minus negative 0.0165 divided by 45 minus 25, and we get 0.0029. After that, we use the formula of Newton forward divided difference and insert all the data from the table, and we get in general form. After that, to find the area of the circle, we just integrate the data using the limit from the x, which is 25 to 45. And then we get the area for the second segment.
This is the discrete least square result, which is the sum up of the step is to sum up the x, y, x square, x cube, x to the power of 4, x to the power of 5, x to the power of 6, x to the power of 7, and x to the power of 8. And then x, y, x square y, x cube y, and x to the power of 4y uh, into the sum it up into the matrix given, which include 5 by 5 matrix, which include x, uh, the n, x, x1, x2, x3, x4, x5, x6, x7, x8, and x8, and then times with the matrix 1 by 5, a0, a1, a2, a3, a4, which equal to the sum of y, xy, x square y, x cube y, and x to the power of 4y. And using the matrix, we can either use the simultaneous equation on the calculator or the on using the online calculator to get the p for x equation. And then you need to integrate the initial x, which is 45, and to the 65 which is the final x, to get the area using the px equation.
In segment 4, we also use Lagrange method because we find it easier and more accurate to use Lagrange for 5-point or a degree of 4.
For 5 segment, we also use Newton forward divided difference, also the same before on the second segment, and then we calculate that to find the area, and we get the area is, after integrate, the area is 1370.0667 unit square. And 6, 7, we also use the same method, which is Newton forward divided difference. Also the same, find the, do the table, then expand the equation and integrate to find the area. The area is 1248.5138 unit square. Now for second segment, The different part from other forward divided different is we use backward Newton backward divided difference. The method is almost the same. First, we form the table from the data and then, but we use the lower part from the table, which is from the 122, 68, 4.5, 0.7, 0.0633, and 0.004. After that, we use the Newton backward divided difference formula and insert all the value and then integrate using the limit from the x to find the area, which is 1.017.0416. For x segment, we also use Newton backward divided difference to find the area, same as the 7 segment. After do all the calculation, we get the area 950.32 unit square.
This is another discrete least square method. The method is also the same, which you need to sum up the x, the y, the x squared, the x cubed, x power of 4, x power of 5, power of 6, power of 7, and power of 8, and then xy, x squared y, x cubed y, and x power of 4y, and put it into the matrix form 5 times 5, which include the x at the end, which is the number of the data, x square, the x square, the x cube, x power of 4, power of 5, power of 6, power of 7, and power of 8. And then there is another terms with the other matrix, which is the a0, a1, a2, a3, a4, equal to the sum of the another matrix of y, the sum of y, the sum of xy, x square y, x cube y, and x power of 4y. And then using that method, you can use the calculator or other method to find the equation. From the equation, you can integrate from 65 to 85 to find the area.
From the 10 segment, we will use the area that we got from this segment to subtract it with the segment number 3. Although we use different method to calculate the area, it does not affect anything, and the area that we use is still valid. We can still subtract it just like any other segment from the upper and lower part of the body.
And now for 11 segment. 11 segment will also use the Newton forward divided difference, same as segment 2, segment 5, segment 6. And after do all the integration, we get the area 236.8333 unit square.
Next is segment 12. In this segment, just like in segment 1, I have divided it in three other segments, which is 1, 12.1, 12.2, and 12.3. In 12.1 and 12.2 is for the lower mouth of the fish to calculate the area, and for 12.3 is for the body behind the head, which we use the area to be subtracted with 1.3 segment. Area for 12.2 segment is for the lower mouth of the fish. In 12.3, we will use this area to be subtracted with segment 1.3. In this two segment, we use the same method, which is Lagrange, so that the calculation could be more accurate since it uses the same method. This means the area might be the same. This is the total area that we got from each segment that we have calculated for, and we show which segment is to be subtracted with it, which segment to get the area of the part of that we are calculating. Just like E1.1 and E1.2 is for the upper mouth of the fish. E1.3 with 12.3 is from the back of the head for the fish. And other is for all other parts of the fish. And for the total area that we got is for the fish image is 1989.1301.
Okay, for the conclusion, we can conclude that the fish image is divided into 12 segments, primarily into 12 segments, but in the first segment, they are divided into 4 segments more at the area of the mouth of the fish because there is a curve on the mouth part. And the three methods used for data characteristic, which is Lagrange, least square, and Newton. Careful arithmetic is critical. Small errors in high degree polynomial can cause a huge wrong answer. Before this, I also have a wrong calculation because of the wrong in power writing, the degree writing in the calculator. The answer can be a millions or thousand. To conclude, we can find the area of the fish by use the upper segment area minus the lower area segment. And then we get the total area of the fish. That's all from us. Thank you.